Okay, so what's the property we want to prove? We want to prove that if W is accepted, then W is in the language. That is to say, if from the start state, I read W and get into S1, that implies W is equal to 1 followed by n many zeros for some n greater than or equal to 0. Now, this direction is really tricky because assuming that W is accepted, you haven't got really much to go on as far as W is concerned. You can't really make many assumptions about W, right? Whereas in the previous problem, this gave us a form for W that we could immediately do induction over. So sometimes, instead of proving this statement, we can prove the equivalent statement, the contrapositive. So we know from the logic part of this course that P implies Q is logically equivalent to not Q implies not P. That's called the law of contrapositive. So instead of proving this statement, I might want to prove the easier statement. If W is not in the language, then it's not accepted. So n star S naught W is not an element of the set of all final states. There's only one final state. So you need to prove if W is not in curly L, then from the start state, I don't end up in S1. And this can be easier because now you've got something to work with. Now you know what the form of W is. So if W is not in curly, so we're going to assume that. So we're going to assume the left-hand side. Assume W is not in curly L. If W is not in curly L, that means W is not equal to 1 followed by some number of zeros for some n, right? For any n, actually. W is not going to be equal to 1 followed by any number of zeros, right? So if W is not equal to this form, what could W be? Well, W could fail to start with a 1. So if W doesn't start with a 1, what could W be? I guess W could be the empty string. Or W could start with a 0 and then some other stuff for some string alpha. Or W could start with a 1 and be followed by a string beta, and beta's got at least a 1 in it, right? Because if beta didn't have a 1 in it, beta would be all zeros, and then it'd be of this form again. So we've got 3 cases to consider. W is empty, W is a 0 followed by some garbage, or W is a 1 followed by some garbage, and the garbage contains at least a single 1. Beta contains at least a single 1. Okay? If beta contains at least a single 1, then we can write beta as some string gamma, a 1, and some string delta, right? Because any string that's got a 1 in it, for example, 0, 0, 1, 0, 1, 0, 0, I can segment this into 3 parts. Here's my 1, here's my gamma, here's my delta. So I should be able to write B as gamma, 1, delta, where gamma and delta are just both strings. They could be empty, we don't know, right? So these are going to be my 3 cases. So I'm going to need a little bit more room to do this proof, so let me get some more paper. Okay. So let's do the cases. So my first case, W is equal to epsilon. So case 1, W is equal to epsilon. We need to prove that W is not accepted. That is, n star of S naught epsilon is not equal to S1. Well, that trivially holds because n star of S naught epsilon is S1, is S0, which is not S1. So that trivially holds because if you're in some state and you read epsilon, you don't move anywhere. So that was easy. Case number 2 is W is 0 followed by alpha. Okay? So n star S naught 0 alpha. Well, where does 0 alpha take me? Well, 0 takes me to T. S naught alpha. Whoops, sorry. T alpha, where alpha is some string. And now if we look at T, we can see that T is a trap state, right? Because there is no transition leading out of T. So if you wanted to, you could formally prove by induction that for any string alpha, n star of T alpha is equal to T. But that's probably overkill. We can just declare, because T is a trap state, that is to say, all transitions out of T lead back into T. Once you're in T, you can never leave T. Therefore, for all strings alpha, n star of T alpha is equal to T. And T is not equal to S1. Cool? So that's the next case completed. Those are the two easy ones. The next one's a little bit more difficult, but it's not too bad. We need to prove case number 3. W is equal to 1, followed by beta, where beta contains at least a single 1. So W's are going to be equal to 1, gamma, 1, delta, where gamma and delta are just some strings. Okay? So we want to prove n star of S0, 1 delta, 1 gamma is not equal to S1. Okay? How can we do that? Well, first off, where does the 1 take us? So if I'm in S0 and I see a 1, I go to S1. So n star S1 gamma 1 delta. I can now apply the append theorem to split off the gamma. So n star S1 gamma 1 delta by append theorem. Append theorem. Okay. Now it looks like I'm a little stuck because I don't know where gamma takes me from S1. So what I can do is I can try cases, right? So there's 3 possible places that from S1 reading gamma can take me. It could take me to S0, it could take me to S1, or it could take me to T. Okay? So n star S1 gamma equals S0 or S1 or T. Now, if we look at the state S0, there's no transitions leading into S0, right? Which means once you leave S0, you can never come back again. There's no arrow pointing into S0. So, because there are no transitions leading to S0, we know that for any other state and for any other string, we can never get to S0. Because if I'm in any state, say S1, it doesn't matter what I read, I can never get into S0 because there is no arrow going backwards. So we can declare for all states S not equal to S0, and for all strings, what letter haven't I used yet? Nu. Nu's a dumb letter. Alpha, beta, gamma, delta, epsilon, eta, zeta, iota, kappa, lambda. Lambda's nice, we'll use lambda. For all states not equal to S0, and for all strings lambda, n star of S lambda is not equal to S0. So for any state that's not S0, namely one of these two guys, and for any string that I read, I'm not going to be able to get back to S0. Okay? So why is that useful? Well, we can use that property here. N star of S1 gamma can be one of these 3 things, but it can't be this one, right? It's going to be one of the other 2. So we'll do cases. N star S1 gamma is equal to S1. Therefore, this term here becomes S1 1 delta. If I'm in S1 and I read a 1, I go to T. And then again, because T is a trap state, regardless of what the string delta is, I can never leave T. This will be T because T is a trap state. T is a trap state. Okay? We've got the other case. Reading gamma from S1 puts me into T. So that was the first case done. Here's the second case. Therefore, this term here is going to become T of 1 delta. And again, once we're in T, we can never leave T. So instantly this thing's equal to T because T is a trap state. T is a trap state. Okay, and in both cases, T is not equal to S1. So what have we proven? We've proven that if W is not in the language, then it's not accepted. And how do we do that? We assume W is not in the language. That means W is not of the form 1 followed by a number of zeros. And we sort of enumerate it by cases. If W is not of this form, that means W is empty. or W starts with a 0, or W starts with a 1, and then it's got another 1 lurking somewhere afterwards. So it's 1 beta, where beta contains a single 1. If beta contains a single 1, that means beta is gamma 1 delta, where gamma and delta are strings. And then for the 3 cases, we proved in each case, the state we end up in is not S1. Therefore, we can conclude, for all W, if W is not in curly L, then from the start state, reading W, we do not end up in a final state. Therefore, we've proven both cases here, and we've formally proven that the language for this DFA is indeed this language here. So that's how you do the formal proof.